100 identical boxes sit in a room, and 100 numbered prisoners are waiting outside the door. Every box holds exactly one slip. Which slip went into which box the warden decided at random. Here is the warden's offer. Open up to 50 boxes each. If all 100 find their own slip, everyone goes free. If even one fails, everyone fails. They get exactly one thing. Time to meet before the game starts and agree on a plan. If each prisoner just opens 50 boxes at random, one person's chance is exactly 1/2. For all 100 to succeed, you multiply 1/2 by itself 100 times. Suppose all 8 billion people on Earth had played this game once every second, starting from the very first instant of the universe. Even then, they still would not have seen all 100 walk free, not once. To see it happen a single time, you would need 364 more universes like that one. And yet the answer is 31%. About one night in 3, all 100 walk free. All it takes is one rule they all agree to follow. And if you blow the puzzle up to 1 million prisoners, that number barely moves. Let's read the rules again slowly. 3 conditions make this problem hard. The 50-box limit, the all-or-nothing rule, and the ban on sharing information. If they could open all 100 boxes, there would be no puzzle at all. That the limit is exactly half is the whole story. The question is not how many prisoners find their slip on average. If 99 succeed and one comes up short, everyone fails. Every box gets closed exactly as it was found, so what one prisoner learns never reaches the next. Let's be clear about one thing. Any single prisoner's chance of success is exactly 1/2, no matter what strategy they use. So the strategy cannot touch the individual. What it can touch is the way all 100 fates are tied together. The real trouble with opening boxes at random is that all 100 outcomes are independent, so 1/2 gets multiplied by itself 100 times. Tie them together the wrong way and it gets worse. Suppose they all agree to open only boxes 1 through 50. The 50 prisoners whose slips sit in boxes 51 through 100 all fail. Not one of them gets out. The probability isn't nearly 0. It is exactly 0. That is what happens when you tie all 100 together the wrong way. So what is the right way? The rule that came out of that meeting is almost disappointingly simple. Start at the box with your own number, then open the box whose number is on the slip you just pulled out. If you are prisoner 37, you open box 37. If the slip inside says 82, your next box is box 82. If that box holds slip 5, you go to box 5. Nothing to choose, nothing to figure out. Swap the boxes for mailboxes in an apartment building and it gets clearer. 100 mailboxes, one letter in each, dropped in at random. Take the letter from your mailbox to its owner. Then take that owner's letter to its owner. Walk long enough and you always end up back at your own mailbox. Here is a small prison with only 12 boxes. Box 4 holds slip 11, and box 11 holds slip 6. Keep following, and on the 6th box he opens his own number turns up. The walk closes right back where it started. Draw in every arrow, and those same 12 boxes split cleanly into 3 closed loops. Prisoner 4 meets his own number and 6 opens, prisoner 1 in 4, and prisoner 2 in just 2. The number of boxes you open is exactly the length of the loop you're on. Short loop, quick finish. Long loop, long walk. This is the heart of the problem. Happily, grade school arithmetic is all it takes. Each box holds exactly one slip. Wherever you are standing, your next stop is already decided. The numbers 1 through 100 each show up on exactly one slip, so exactly one box points to any given box. There are only 100 boxes and the path never breaks, so sooner or later you step on a box you have already opened. But every box has only one way in, so the first box you revisit has to be the one you started from. The only box that points to your box is the box holding your own slip. Follow the loop and your number always turns up. The question is whether it turns up within 50 opens. Could you ever open the same box twice? That would take 2 slips with the same number, and each number is on just one slip. So one thing decides a prisoner's fate. Is his loop 50 or shorter, or is it 51 or longer? Now it is time to count the probability. Here the problem turns strangely clean. An arrangement can hold at most one long loop. 2 loops of 51 would need 102 boxes, and there are only 100 boxes. So the whole story gets very simple. The road forks exactly 2 ways. If the loop is 68 long, exactly 68 people go down at once. That leaves one question. When the slips are shuffled at random, how likely is a loop like that? The answer is startlingly simple. For a loop of length 68, the probability is exactly 1 over 68. Why does it land so exactly? Pick the boxes that go on that loop, string them into one chain, then arrange the rest. Multiply those counts, and you get the total number of arrangements divided by exactly that length. It also means the chance that all 100 boxes form a single loop is exactly 1 over 100. So the chance of failure is 1 over 51, 1 over 52, all the way to 1 over 100 added together. That sum is 0.688. So the chance all 100 walk free is the rest, 31.18%. The top of the figure lays out 8 randomly shuffled nights, with a bar for every loop length. Some nights the loops break up small and everyone lives. Other nights a loop of 90 swallows the whole board. Bottom left is where the longest loop landed across 200,000 nights. Bottom right cuts the probability into its pieces. 200,000 simulated nights line up with the math exactly. And here is a slightly chilling fact. The most common failing length is 51. Nights where they fall exactly 1 box short and all 100 stay locked up come around more often than any other length. Look at the peak on the left. The longest loop averages 62.7 boxes, and the median is 61. This strategy does not make bad luck rare. So what on earth did it change? Now for the real twist in this problem. Even with this strategy, your personal odds do not budge. Your loop length is equally likely to be anything from 1 to 100. So the chance my loop is 50 or shorter is 50 out of 100, exactly half. Either way, an average of exactly 50 people fail each night. The total does not move. And yet the odds for all 100 of them jump from essentially 0 to 31%. So what actually changed? The failures clumped together. Open at random and failure scatters. Follow the loop and it all piles into one loop. For anyone to fail at all, at least 51 people have to fail at once. The chance that prisoner 1 and prisoner 2 both succeed is 0.376. If they were independent, it would be 0.25. Opening at random is like flipping 100 coins one at a time. Following the loop is like bundling them into one block and flipping just once. Nobody is signaling inside the room. The information was written into the arrangement of the boxes from the very start. The game is decided before the prisoners ever walk in, at the moment the warden drops the slips into the boxes. Shake the rules a little, and you can see exactly what this 31% is resting on. Gray is opening at random and it bunches up near 50. Blue is the loop strategy and it plants a tower right at 100. Everything between 50 and 99 is completely empty. A night like that simply cannot happen. Give them 10 more boxes and it jumps to 49%. Another 10 and it's 65%. Tighten the limit instead and it collapses fast. A smaller group actually does better. Multiply the crowd by 10,000, and the answer barely moves. It does creep downward very slowly, and it settles at 30.685%. That number is 1 minus the natural logarithm of 2. And the 2 there is 100 boxes divided by the 50 they get to open. If the guard can swap the slips in just 2 boxes, he can guarantee 100%. Swap 2 boxes on the long loop and the loop gets cut. Cut it near the middle, and both pieces come out at 50 or shorter. But pick the wrong place to cut, and you only make things worse. Now flip it around. If the warden knows the strategy and builds one loop of 100, the probability drops to 0. There is a counter to that. They draw one random relabeling that links numbers to boxes, and all of them memorize that same table. That brings the odds back to 31.18%. But if they each pick their own relabeling, it's essentially 0 again. This puzzle wasn't born in a book of brain teasers. It came out of a theoretical computer science paper. It was a 2003 paper by Anna Gall of the University of Texas and Peter Bro-Miltersen of Aarhus University. The puzzle sat in a short footnote after the proof, and its original form was a little different. The two wrote that if there are at least twice as many boxes as slips, the chance of winning shrinks exponentially. By Winkler's account, Milterson himself believed there was no answer. The one who turned it all around was his colleague Sven Skyum. He said that with no empty boxes, the success rate holds near 0.3. The paper never wrote that method down. It left just one line. The prisoners in boxes costume came later. The problem passed through Dorota Hernov and reached Winkler. Curtin and Warschauer proved that no strategy beats following the loop. 31.18% is the ceiling. In 2022, a Veritasium video spread this problem across the world. This problem has lasted not because of the answer but because of how the answer comes about. The prisoners didn't raise their own odds one bit. All they did was bundle 100 separate gambles into a single gamble. We're taught that slicing risk into small pieces is a virtue, but this room works the other way around. Failing big when you fail is the only way everyone walks free together. Something that would take 364 universes became a 1 in 3 event, and nobody took a bigger share. The instinct that everyone doing their personal best adds up to the best for everyone gets betrayed all the time. In this room, luckily, it broke the right way. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.